All right, so we are going to just get right to it because this class is probably the longest class that we're going to have this semester. Um, we're going to go over some things related to the class and assignments, and then we're also going to go through statistics, which I'm sure you guys are super excited about, especially at 8 o'clock at night. Thank you so much for joining me, and thanks for rescheduling this. I very much appreciate it. Last week would have been very difficult for me because I was out of town. So appreciate it. And without further ado, let's get started. So what I wanted to do was talk to you a little bit about assignment number 5. So I have it up on the screen. I'm going to share my screen right now. And so that way you will be able to see it in a moment. And I'd like to hear if you can see it, please. Please let me know if you can see what I'm sharing with you. You guys see that? Yes? Everyone sees it?
Yes, sir.
Yes, Professor.
Good. Okay.
Yes.
Great. Thank you. Okay. So assignment number 5 is a little bit different than the other assignments. And here's where we're really starting to talk about what types of information appears in a journal article. More specifically, what kind of visual information appears in a journal article. So what I'm asking you to do here is, for each set of the results that are presented to you, I want you to tell me whether or not you would put this in a table, would you put it in a line graph, or would you use a bar graph? Now, you could choose the same type of graph for each one of these examples, and there are 3, or you could choose a table for one, a line graph for another, a bar graph for another, or vice versa, or however you want to do it. But in addition to choosing the type of visual representation, I want you to explain why it is you chose that visual representation. So it's really important to understand that when we look at data, especially in graphic form or in table format, we need to have that data tell us a story. If it doesn't tell us a story, then it's not represented correctly. So if you are reading a journal article and you're looking at a graph and there are, bars all over the place with all different kinds of colors and very, very difficult to make out anything, the person who created that graph did not have in mind the idea of telling a story of the data. That's what you want to do. You want the person to be able to pick up by using a graph. What does this data tell me, right? What are the differences in the bars, and why are those bars, why are they different? What is there a significant difference between the bars? Is there a small difference between the bars? Or if I'm reading a table, can I easily see the categories that are being compared? Depending upon the type of research you're doing. So looking at something like this, right? Looking at, cardiovascular risk factors as it relates to growth factors. So these are specific types of factors that are measured in the blood that may be related to cardiovascular risk, specifically in diabetics and smokers and drinkers and in people with high blood pressure. Does this table tell me a story? Am I able to kind of decide like what it is I'm supposed to be seeing here? Can I see differences between groups very, very easily? And so that's really what you want from a graph or from a table or any kind of visual representation. Now, one of the things we're going to talk about today are all the different kinds of graphs that are out there. There are pie charts, there are scatter plots, there are box plots, there are bar graphs, they're both vertical and horizontal. There are line graphs, there are area graphs. I mean, there are so many graphs. Not to mention, if you use a software program, You can make your graph into any color. You can, create it in a 3D format. There are so many types of things you can do. But I think the bottom line is that whatever graph you choose or whatever visual representation you choose, it needs to be clear and it needs to be informative. Otherwise, the person's going to look at it and have absolutely no idea what they're looking at. So that is key. It's a key point to today. And I think it also speaks to what we're going to talk about when we talk about statistics. So today's objective is to look at some very basic statistics, just kind of, how do we, I know this is probably a review for you, but I think it's a good, sort of, it's good for developing your fundamentals, right? And then we're going to talk about, we'll talk about the basic statistics, and then then we'll talk about the types of tests that we can do. And I have a couple of videos that I've been kind of reviewing over the last week that I think are helpful. And they explain sort of these types of tests that can be done. And then we're going to take a look at graphical representations and see what kind of graphs do we use for what kind of information. And that should help you when you do this assignment. You'll be able to look at this and say, yeah, that doesn't really fit a table, or that doesn't really fit a bar graph, or, I only have you looking at 3 kinds of visual representations. I could have put in there pie graphs and all the other ones, but really a table, a line graph, and bar graphs are usually the types of graphs that you will see in most scientific journals. You may see other ones, as I mentioned, scatter plots and box plots and things like that, but tables, lines, and bars are very common. So that's why I associated it with this assignment. So does anyone have any questions on anything I talked about related to assignment number 5?
No, sir.
Do you want us to make
It's perfect.
Yeah, so
Professor,
that's a great question.
I have a doubt.
Let me answer. What's that?
Yeah, so Professor, in the assignment 5, you just have to mention that which graph or table would be appropriate and the reason for it. That's it, right?
Yeah, so it's a great question. I have had students in the past create graphs with the data.
Okay.
It is not, I'm going to tell you that is not necessarily part of the assignment. So I'm not going to grade you on how you make the graph. That's not the point of the assignment. What I do want you to do is tell me what visual representation you're going to use, and then give me your justification for using it. That's what I want you to do. If you want to create your own graph with the data, great. I think it's a really good way to practice. It also indicates that you have a very strong knowledge of what it is you're doing if you can create a graph from the data I'm showing you. But if you don't, that's okay. Again, all I want is just the type of graph you're going to use and the justification for why you chose that graph. Does that sound clear?
Yes.
Yeah,
Thank
thanks.
you, Professor.
Great. Okay. So this class, I've gone back and forth with this particular class because it's usually the longest, as I mentioned. And, with individuals like us, human beings with a very small attention span or short attention span, this class tends to get long-winded. So what I've tried to do is break it down a little bit. Now, you have the presentation, and that's fine. You can go through that on your own, and you can look at it. And if you have any questions about the presentation, you can ask me, and that's okay. But I'm only going to use the first few slides of the presentation to just go through some of the basic statistical terms and what they mean, and sort of how they fit into statistics. We'll talk a little bit about mean, median, mode, standard deviation, and then from there we're going to deviate I'm going to give you guys a little bit of a break, maybe 5 minutes, and then we're going to go back and we're going to take a look at some videos that look at how is the data represented, right? So it's one thing to be able to do a calculation and determine a standard deviation. And we'll go over what that is if you don't know. But to teach you calculations is not really, to me, that's not necessarily very applicable. You could just take that calculation at any point in time and use it. You could look it up in a book. You don't even need this class to do that. And you could figure out, you know, what that standard deviation is, what that number is. But what I want you to really get out of this is, what are the basic statistics and why are they important? And then in addition to that, once I know that, then how do I tell the story in a visual representation? So whenever you read a results section of a journal article, you'll see statistics out the wazoo, right? You'll see all of these kind of parentheses and plus and minus and F scores and Z scores and all of these statistics. But really the bottom line that you want to know is, what's the comparison here? What group did better? What group did worse? And what story is it telling me? So that's really my objective here. That's what I want to get across to you. So before we start, any questions? Okay, I'm going to open up the presentation. Gonna just take me a moment to grab it. And let's open this. See if it opens in my downloads. Maybe it does, maybe it doesn't. There it is. Okay, perfect. All right. So the presentation that you guys have, all right, go through. I want to make sure it's the right one that you have. Week 11 presentation. I think I changed it actually. So originally it wasn't this one. It was a different one. So I'm going to pull up the other one that I used, and then of course if you want to look at this, you can, you know, feel free to look through this presentation. But I'm just going to pull up my the one that I used for last semester. So we are in, here we go. Okay. Yep, okay, this is it. So this is a presentation that I've done for all of my classes. And like I said, it's a little, you know, it's a little sort of heavy, but we'll go through it slow. I'm only going to go through a part of it, and you'll see what I'm talking about once we open it up. Okay, so this is, whoops, let's go back here. Let's go back. I think I'm too far down. Okay, so this is a presentation on quantitative statistics for research methods. Here are some, if you really want to get into it, you know, here are some really good books and resources on statistics. And I think Statistics for People Who Think They Hate Statistics is a really cool book. It's good. You know, it's a little bit less serious and formal than some other books. And I love the title, and it's a really, really cool book. All right, so we're going to talk about some types of data first. We're gonna look at what variables are and how they're broken out. So let's first start here. Whenever we do a research study, we are going to have variables. These are the things that we are going to measure, right? They're the outcomes. They're what we want to see changes in, or possibly it could be an environment that we create, or a temperature we use, or anything that will influence the outcome of our study. These are known as variables. Now, what kinds of variables do we have? There's two different kinds, just like in a sense, there's two real types of study data, right? There's quantitative study data, which really refers to numbers and objective information that is measured from the let's say, a physiologic perspective, you're measuring actual numbers, and I'll talk about that when I talk about ratio and interval. Whereas qualitative is more subjective. We're getting information like emotion, opinion, usually semantics. It usually has to do with words and not as much with numbers. So when we look at these two and we break them out, we say, okay, well, quantitative types of data, there's two of them, two common ones. One is ratio and the other is interval. So what does a ratio mean? Well, ratio is any relationship. So we could be looking at pulse rate and height. We could be looking at height versus weight. Let's say we're looking at, cardiovascular risk as it relates to waist to hip ratio. That is a ratio. So normally what we're doing is we're taking one number and dividing it by another, and we're getting a value, right? Or we could look at interval. Interval has to do with a range. So in this case, they're using degrees. So 36 to 38 degrees Celsius. We could use Fahrenheit. We could use blood pressure ranges. So anything from pre-hypertension to somebody who has, severe hypertension. So those quantitative types of data are what you're going to see. And again, these are based on the variable that you are measuring. So just types of data. Now, when it comes to qualitative, there's ordinal and there's nominal. Now, ordinal is really categorical. So it means like if we're looking at social class, so we're looking at, let's say, lower, middle, or middle and upper class, because we're measuring we're measuring purchase prices of real estate in a certain geographical area. So we're going to look at classes and we're going to categorize those classes, and that's a qualitative type of data. Hold on one second. Okay, I'll open it. Yes, I will close it. Sorry about that. And then the other kind of data we have is nominal data. So nominal data is things like gender, so male, female, ethnicity, not necessarily categorical, but more in the sense of like an either or type of situation. So these are the kinds of data that relate to quantitative and qualitative variables. Now, when it comes to looking at data, we have to figure out where our data falls, right? So we have to determine, based on the information that we have, where is our data in relation to, let's say, a larger population. So I'm going to give you an example. We're going to do a study on the effect of a special kind of strength training that just came out. And someone invented it, and it involves, all the different muscle groups, and it's this real inventive, innovative kind of strength training program. And we're going to look at that strength training program in 50 people who have never strength trained before, and then in 50 people who have strength trained in the past 6 months, and then 50 people who are avid strength trainers. And we're going to see what kind of influence this new innovative strength training has on these three groups. So what are we really looking for? We're looking for a comparison between the groups. How is it that the groups differ from one another? And for some reason, the bell curve is not here, but let's see if it doesn't pull up. I think we're on like a little technical difficulty here on this. But okay, so going back, what we're looking for in our data is what we call a normal distribution. What does that mean? Well, when we look at the numbers, so what is it we're measuring in response to strength training? Okay, we're going to measure quadriceps strength, and let's say upper body strength. And what is that measure going to be? It's going to be the amount of force that someone generates with their quadricep during a leg press, and then it's going to be the amount of force an individual generates during a bench press. That's what we're doing. So we're going to look at force. We're going to look at, if you're not familiar with the term watts, W-A-T-T-S, it's a measurement of energy. So what do we want to find? We want to find a difference between the three groups, right? Between group one, which never did any strength training, group two, which strength trained in the last 6 months, and then group three, which is an avid strength training group. And we probably want to see the most influence of this new innovative strength training program in the ones that didn't strength train ever. That's what we want to see. But what we're looking for at the first glimpse is, what are the averages we are seeing in terms of the force generated during leg press and during a chest press? What are the averages in these groups? The average is known as the mean, right? How do we get the average? We basically take the number of values that we observe and we divide it by the number of values in that observation. So the number of values we observe, and we add them up and divide it by the number of values in that observation. And so once we get the mean, we have an idea of where each group stands in terms of their strength, right? In terms of how much force they're generating. But the real key is when we are looking at the data, we also want to see the spread of the data. So how wide is the data set? And so the normal distribution, okay, if we're defining these types of descriptive terms of statistics, we have the mean, which is the average. We have the median, which is the value that comes halfway when the data are ranked in order. So let's say, for instance, we had 50 people in our group, and all those people, did their exercise, and everybody was compliant with the study, and we got all this data. And so we want to find out, what is the median of this force, right? The force is the number we're looking for. What's the median? We're going to count the number of people in our group. We're basically going to put them in order, right? So lowest force to highest force, and then we're going to take the halfway point. And that's it. That is not the average. That is the median. Median is not often used when it comes to, research articles and journal articles, because it's not as informative as an average would be. And then the mode is the third one, which is also the most common value observed. And maybe if you're looking at things like frequency and you're looking at number of kids who scored a certain, test score in a class, mode might be helpful. But when it comes to force generation and you're looking for a comparison between three groups, mode is often not reported. So we know that the average is really what we're interested in. But more than that, we're interested in the spread of the data around the average. So this is known as the standard deviation. Now, for some reason, these little graphs are not appearing, and I'm not sure why. So what I'm going to do is just shut this and open it again to give it another. Yeah, it's not showing. Okay. So what we're interested in is the spread of the data. When you guys open it on your end, you'll be able to see it. And what does that really mean? What is the spread of the data, and why is that important? Okay, so think about it this way. You have 50 people you've tested. Now, out of those 50 people, 15 of those people, so 30% of those people have numbers, the force generated, have numbers that are so far from the average, they don't make any sense. So maybe you either in one of your groups mixed up your subjects and you got somebody who's an avid strength trainer in a non-strength training group, possible, or your equipment is broken. You know, whatever you use to measure that force, it's not working correctly. And when there's a great amount of spread of data around the average, it really takes away the influence of the data. So when there's a lot of people that are not close to where the mean is, or a lot of, you know, subjects or participants who score in a way where it's not close to the mean, there's a greater spread and a greater standard deviation. Well, we don't want to really deviate from the mean that much, right? We want to stay as close to the average as possible, because that indicates that our data set is not only influential, but it is set up in such a way that the data can say something about the innovative strength training or about the group. If there's a group of people that are so far from the average it doesn't make sense, then the data doesn't make sense. You have to look back and see why it is that occurred. So when we talk about the spread of values around the mean, we are focused on what's known as the standard deviation. Here is the equation of the standard deviation. It is the sum of the values multiplied by each value. So meaning you're taking subject 1, subject 2, subject 3, each value, and you're subtracting from that the average, and then you're squaring that number. That's the first thing you're doing. Then you're dividing that value by the number of values you actually have in your data set. So it could be 50, it could be 25, you know, however many values it is. And then you're taking the square root of that. Now, to go through this equation, you know, yeah, I mean, it's important to know, but like I said, you could look this up in a book and you could figure out, you know, what your standard deviation is based on your data set. The key that I want you to understand here is the smaller the spread of values around the mean, the more influential the data set. The wider the spread, or the larger the spread around the mean, the less influential the data set. Now, I'm going to ask are there any questions? I'm going to stop here. Please do not feel at all, you know, hesitant to ask a question. I really want you to ask questions. Again, as I said, this class is probably the heaviest class, you know, of the course. Please, I'm open to any questions. I hear crickets. Not a question, not one. Are you still there? Is everyone still there?
Yes, sir.
Okay, I'm glad to hear that you're still there. Not one question. Should I continue? Hello?
Yes, sir.
Okay. All right. I'm going to continue on. And I'm a little bummed that it doesn't have its, our little, something's wrong. Hold on one second. I'm just gonna see if I can find another copy of it that's a little bit better. Fall. Let's try this one. Same thing. Yeah. Very strange. Okay. Okay. I wonder if, you know, if you give me 1 second, I'm going to try to pull it up from the, not from the assignment, but 1 second. Let's try this. Content. Go into presentations. Go into this. Yeah, all right, I found it. Okay, good. So I'm going to share this one with you instead, because at least this way you can see what I'm talking about when I'm talking about standard deviation. Okay, so we are going to continue. And now for those of you, like I said, this may be somewhat of a review, but I do think it is important to talk about this. Okay, so this is what it really looks like. So the normal distribution, right, as we discussed. Here's that mean value, that average value, and then this is the spread of the data. So what this bell curve really represents is where the data falls on these axes, right? So we have the x-axis and the y-axis, and so here, let's say we have force generation here. So the amount of force that's being generated. So that's where these numbers lie. And so we have an average amount of force generated. And then we have some people who generated a little bit of force and some people who generated a lot of force. Now, what do you think we have on this axis? What could we possibly have on this axis that would be in relationship to the amount of force generated? Does anyone know? Want to take a guess?
Can you repeat the question?
Yeah, what would we see on this axis? What would be over here? What would an example be that we could put on this axis? Anyone?
We can put age over there.
Put which?
Age.
Age?
Yeah.
Yeah, we could put age. That's a possibility. Could we put the amount of time for training? How many months an individual trains? So what would that indicate if we did that? So here we started 0 months, and here we go to, I don't know, 16 months. What would this data tell us? What would this bell curve tell us?
There was like the biggest increase in the middle months of the training.
Could say, okay, so because of the ramp, you mean, because of this, we're seeing an increase here?
Yeah.
Right, so we could see between how many months, right, do we see the greatest increase in force production? We could also see where the peak is, right? We could determine like an individual who trains for 12 months, has the highest peak in force production. That's a possibility. We also see a law of diminishing returns though, don't we? We see a decrease here too at some point. So again, what you put on the axes also helps to tell the story. So if we want to just look at force in relation to the 3 types of groups, we could do that too, right? We could look at the force here from low to high and then split it into the 3 groups, which we'll see in a moment. But the key to this is that the more the data is further away from the mean, the worse the data is, right? And the less it tells us. So again, here we went over this equation, but when we have a normal distribution of data, which doesn't always happen, but for the most part, I would say data is around a normal distribution. It may not look exactly like this bell curve, but it's sort of in the vicinity of the bell curve. It has a similar shape. When we look at a normal distribution, there is 95% of the values fall within 2 standard deviations. So let's look at that again. Let's say, for instance, we have 210 people in our group. 150 of them will fall very, very close to the average. Again, this is a good data set. I'm not saying that it's every data set. About 50 of these individuals will fall within 1 standard deviation of the mean. And then about 10 of these individuals will be way outside. So some will be around the mean, but many, many, many will be outside of it, or outside of those standard deviations. So why is standard deviation so important? All right, let's think about this. So we do our little study in our lab, and we have, I said 150 people. So we had 50 people per group. And we go and we publish, we go to a conference, we're so excited. We go to Chicago to this big conference and we present our research, and someone says, okay, you studied 200 people, 50 in each group, 50. So 200 total, I'm sorry, 100, what did I say? 150 total. 150 total, 50 in each group. Do you think those 50 people are representative of the larger population of millions of people? What would your answer be to that?
Definitely not, unless the study group is rare, like the condition is rare, or accordingly, whatever the study that the person is doing is
yeah,
rare.
meaning when you say rare, you mean not found in the larger population.
Yeah, but if you're talking about general public, then 50
Right.
people or 100 people are not going to represent millions.
Okay, but I say to you, well, but yeah, my study's significant. I found significant differences in the 3 groups that I tested. Now, the important part here is that overall, you tested 150 people. That's wonderful. You got 50 people to come in for a training study. You should get a medal. But the reality is it's not very representative of the larger population. So when you're looking at something like this, as the sample size increases, the standard deviation goes down. Why? Because you are now, as your sample size increases, you are now starting to represent a much larger population. So instead of 150 people, you tested 15,000 people. Well, now your data set says something about a population. I mean, look, it's not, in reality, it doesn't compare to millions and hundreds of millions of people, but you could say something if you tested thousands and thousands of people. Look at any kind of pharmaceutical study. They have to go through various stages of the clinical study, and in each of those stages, they're testing thousands of people for the efficacy, the effectiveness of the study, as well as the safety. The efficacy of the pharmaceutical, the drug, as well as the safety. They can't test 150 people. That would be ridiculous. So the greater the sample size, the tighter the data set, the closer the data comes to the average, to the mean, okay? So when we look at a skewed distribution, this means it's skewed to one side. So the average is not in the middle as it is here with this red line, but it's actually skewed to one side. Does anyone know what would cause a skewed distribution? I'm open to anything. Does anyone? Come on. what do you think would cause the distribution to slide over to one side, either the left or the right?
A positive relationship.
What would have to happen?
Or a negative relationship.
Wait again?
A positive or a negative
You have to say it
relationship.
again. Well, yeah, that's true. So positive or negative relationship between two variables, is that what you mean? You're thinking a little bit more
Yes.
along the lines of like a correlation, right? Relationship. But why would 50% of the values then lie on the on either side of the mean, but not in here? 95% of the values lie on either side of the mean. What's happening in this case?
Professor sampling bias?
Possibly. In what way? What do you mean? What do you mean by that? In our training study, what would have to happen? What do you think would have to happen to get this kind of skew? You were on to something, so continue.
Like collecting the data which is available easily?
Think about the groups. What would have to be wrong with the groups in order to get this kind of weird distribution?
Maybe the groups are not equally divided and one group
Yeah.
is like 100 and other is 20, 30 or something like that.
That is a possibility. Also, what about the characteristics of the group? Remember, I said one does an exercise, one's within 6 months, and one's an avid exerciser. What if there were mixes and matches in the groups? And you had some non-exercisers in the 6-month group, and you had some avid exercisers in the non-exercise group. That might skew it too, because the outcomes wouldn't be true in relation to the characteristic of the group, and therefore the distribution could possibly be skewed. You may get more of that, maybe you get more of the low force values kind of like in one spot, and that just shifts everything to the left, or you get really high force values in one spot and that shifts everything to the right. So skew does happen, but again, look, it's not like if your data is skewed, oh my God, you're screwed. That's not what this means. It does mean though that the data is telling a specific story here, and there is not a normal distribution, and that really, it makes it difficult for you to make your argument. You can make your argument, but it makes it more difficult. And let's look why it makes it more difficult. So when you're looking at a normal distribution, things like height, weight, hemoglobin levels, that's fine. When you're looking at skewed distributions, these are things that are not necessarily the same across the spectrum, right? Like bonuses, right? Could be really, really high in one place and really, really low in another. Number of marriages is another example. So it's not that it's bad, it still tells a story, but you definitely have to work a little bit harder to make the argument. So I'm going to let you guys read through this because this is on, this is in your class. So we're going to go through just an example of how standard deviations really play a role in how it is that we determine whether or not our statistics are appropriate. Okay, whether or not we could also even get to the point where whether or not our statistics are significant, the data is significant. So here we tested a sample of people on an IQ test, and it's been standardized on a large sample to have a mean of 100 and a standard deviation of 15. So what that means right now is that the average score on this IQ test is 100. Some people score 115 and some people score 85. So between the 85 and the 115, we have basically one standard deviation. Does that make sense? right? So we have a mean of 100 and a standard deviation of 15. Okay. Any questions? All right. So now you administer the test to repeated samples of 25 people. Remember, we did a test on a large sample. We didn't say how many people, but now what we're going to do is we're going to take 25 people from here, 25 people from here, over here, and we're going to give them the test. And we're going to then expect that there will be variation in their scores, right? This is known as the standard error. Now, what that means is when you take one sample size, so in this case, you have a large sample size and you basically give an IQ test to a large sample size. And as I said, you have an average and you have standard deviation on both sides. But then you're going to take that test and you're going to give it to pockets of people, and then you're going to compare the means of those pockets of people. They scored an average of this, they scored an average of that, they scored an average of this, and they scored an average of that. The variation in those numbers and those scores is known as the standard error. Well, how do we get that? Again, another equation, which is you take the standard deviation, that number, and you divide it by the square root of the sample size. In this case, our sample size was 25 people. We take the square root of that number and we divide it by the standard deviation, which we said was 15. The standard error is 3.0. Now, it's important to understand that the standard deviation and the standard error are associated, but they're not the exact same thing. Because the standard error, all right, it's the error or the difference or the variation of the mean, and it's an estimate, as it says here, the variability of various populations. So it basically is an estimate of how precise the sample mean actually is. So when we talk about the standard error, we're really looking at different populations and the means within those populations comparatively, like comparing the means of each one of those populations. Whereas when we look at the standard deviation, is a measure of the variability in a sample. Now, I don't want to, I know it's confusing. We could do the standard deviation of those 25 people as well. We could do that. That's fine. But that's in those 25 people. That is not comparing those 25 to these 25 to these 25 to these 25. So how does this relate then to our example that we looked at? We have 150 people. So in our data set of our innovative strength training study, we are looking at 150 people across the board. We're going to get an average, and then we're going to get a standard deviation on both sides of that average. But then we're also going to measure the mean of group 1, who does an exercise, group 2, who exercise within 6 months, and group 3, who are avid exercisers. Remember, there's 50 people in each one of those groups. By looking at the comparison of the mean between those 3 groups, we then get our standard error. Now, the key is that the standard error should not be that high. Because what do you think it says if the standard error is actually quite high? What does that say about the groups themselves? We're going to take a break in 10 minutes, but what does it say about the groups themselves? Come on, you guys know this. If the standard error, the comparison between the averages of the groups, is high, what does it say about the groups? Is everyone still there?
Correlation?
Wait, it says what? What do they say?
A weak correlation between the variables.
Did you say a V correlation?
Yes, Professor. I'm not sure.
What? That's okay. It's okay. You're the only one answering. Give me someone else take a stab at this. If the averages between the groups indicates a high standard error, what does it mean about groups?
That means the,
Consider it, yeah.
yeah, okay. Uh,
Go
I
ahead.
wanted to say that if the standard error, like the average difference between both the groups is like high, then I think the groups are not equally divided, or the
Yes.
selection criteria is at a fault where
Right.
where the examiner didn't gave a proper selection criteria for each group or overall study groups, because of
Right.
which the average got so different.
Now, in a way, you want to see a difference between those groups, right? You want to see a difference between the non-exercise, the 6-month, and the avid exercise. You do want to see that difference. But with a higher standard error, you're basically saying the groups are not, they're not really equal. They're not, characteristically, they're not the same. Fine. So
Why is 3
No, go ahead.
considered? Why is
Why
3
is what?
considered a high standard deviation though?
this is not a high standard error necessarily, but it is the error that was determined by this sample. But it's not necessarily high. It just indicates the variation. You know,
Okay.
you could have a standard error that's a 10, you know, so it's not, it really depends on what these numbers are that are going to give you that standard error. So
So
if
just
you
in
have a
terms of like
really
your example?
Yeah, so the higher the standard error, the more variation there is within the groups. Like, or I should say, my fault, between the groups, not within the group. So let's just talk about that for 1 second. When you look at a standard deviation, you're looking at it within the group, within the large sample size. The sample size of however many people you're testing, 150, 50, 2,000. When you're looking at the standard error, you're looking at the variation between the groups. Does that make sense? So again, they are associated measurements, but they are different and they tell a different story.
Okay, I got you.
So,
Not really a
so far,
math
so good?
person. Yeah.
It's okay. It's okay. It's not, that's okay. So let's look at this example again, taking the IQ test. So now you've got a sample of 25 people, as we said, they get a score of 107.5. What did we say? We said that it goes from 185 to 115, right? So what are the chances of obtaining another IQ score of 107.5 or more in a sample of 25 people coming from the same population as that test was standardized? So meaning you're basically looking at this entire group and then you're taking 25 people and they score a 107.5. What are the chances? Well, if you're going to look at the chances, right, then you're going to look at how does the sample mean, meaning the average of the entire sample, minus the population mean over the standard error. This is the equation that's going to give us how far out on the standard distribution we are, right? So if you're looking at, and again, this number can be really high, which indicates there's a huge variation, or it could be really low. But this tells us how far away we are from the population mean. It tells us basically either we're close to the average and then our data set is tight, or we're really, really far away. So if you look at this 25 people who scored a 107.5, they are pretty far from the mean. Means they're smart, right? They're smarter than the average person who took this IQ test. So now let's just go to here for a second, because again, I think it all relates to, it all relates to the same thing. When you look at the area here, this little part here under this tail, under the gray tail, if we're looking to see what kind of chance is it that that 25 people would score an average of 107.5. So how do we determine that? Well, we have to figure out, number one, what is our standard error, but we also need to look at what is the ratio in terms of chance. So this is where we get into a p-value. Okay, and this is key, because I think this is very applicable to any kind of research that we're ever going to do, we're ever going to read, we're ever going to see. How is it determined then that we have a 1 in 160 chance of scoring 107.5? How is that possible? How do we know that? So let's take a look. So what we're basically saying here is that when we are going to measure, I'm going to go back here for a second. When we're going to measure I want to go back to this one here. Okay. Yeah. When we're going to look at standard deviation and where either IQ scores fall or where, strength numbers fall, doesn't matter. As researchers, we basically want to say, look, we predict that all of the values that we measure will fall within 95% of 2 standard deviations of the measurement. So meaning all of the people who I test, the 50 people who I test, 95% of them will score within 2 standard deviations of the average. Why am I doing that? Because it tells me that I am confident in my data, but it also tells me that there's a 5% chance that there are going to be individuals who score outside of those 2 standard deviations. So there's going to be some very, very strong individuals in my group, or smart if we're measuring IQ, and there's going to be some weaker or not as strong individuals in my group, or don't do as well on an IQ test. Why do you think 95 is the number that we fall on? What is the point of 95% confidence? And this leads to what we were talking about before, determining the chances. This is where we ended up. Why do we use 95%? What is that? What is it telling us as people who read researchers as researchers? What does it tell us?
It tells us that the research is 95% correct and 5% error is acceptable.
Okay, why? Why do we use 95%? Why don't we use 99%? How come we don't use 98%? Why don't we use 60%?
Well, I believe that depends on what the topic the researcher is picking up. He can determine how much error he wants to be in his study. But
okay. But why is 95% why is that the convention? Why is that the standard?
I don't know.
It just gives you a perimeter with like 5%
yes.
of like a random error.
Yes. It gives you a cushion that is reasonable. What if it was 90%? What would you say to that? 90%. So you're instead, you're reading research and the author says, our p-value was significant at 0.10. So 90% confident, but not 95. Does that tell you anything about the data?
Maybe 90% there might be some error in data collection itself because um, the samples were not up to date, like they did not participate to that level, or might be that the participants were not up to mark, like whatever the criteria that he had set for
Mhm.
the study, they were not achieved, or they were not able to bring it to that point, maybe.
Yeah, but the one thing is that you set that number before you do your study. So you don't know how your subjects or your participants are going to behave. You don't know what your data is going to look like until it comes out, until you have, until it's finished
The
and
results.
you look. So we don't set it at 90% because it doesn't communicate the kind of confidence that we need to see in research. Now, if it's 90%, it's like, okay, yeah, there's a 10% chance it didn't work. That's not enough. I need to know it's 95% confident, or 95%, I'm using a parameter of 95%. So my only cushion is 5%. That way, if something is significantly different, there was only a 5% chance that it wouldn't be. And so that gives us a little bit more confidence when we read research, when we do research. And that's why the convention is considered 95%. That's why you always see a p-value of less than 0.05. We'll talk about that in a second. So when we're looking at the p-value, right, in this case, we said, based on this calculation, we said there's a 1 in 160 chance that these 25 people would score an average of an IQ score here. So that means that it's 0.006. That's the ratio. And what does that equate to? That equates to a p-value of 0.006. So is that less than 0.05? Yes, it is. So this would be considered a significant difference of an IQ score from the average. Now, what is a p-value really refer to? It refers to probability. What is the probability that the IQ score that we see, that in our example, the force generated in one group versus another, what is the probability that the change that you are seeing, or the value you are seeing, is due to chance? What's the probability of that? What is the probability of it just being variation due to chance, due to the flip of a coin? Has nothing to do with how smart someone is in the IQ test example, has nothing to do with the innovative exercise program or strength training program we implemented, nothing. Just a flip of a coin. You would have gotten the exact same answer. So when we look at a p-value, we are really expressing what is the probability that we see this change as a flip of a coin, or what is the probability we see this change due to an innovative exercise program, due to smart people who take an IQ test, or whatever it is that we're measuring. So the example is that once we start to then move closer to the average here, the green moving closer to the red, what do you think happens to the p-value? What happens to the probability of the green getting closer to the red? Does the probability increase that that's going to happen, or does the probability decrease that that's going to happen?
Increases.
Why is that? Why do you think?
There's a larger amount of people, like averages there.
Yeah. So you've taken a large sample size, and this is your average. So people who go closer or get closer to the average, there's a higher probability that that's going to happen. You're going to have less of a probability of people being all the way to the right or all the way to the left. So again, when you're looking at data and you have, you know, these data points that are so far from the average, it's a very low probability that that's going to happen, right? And so you want to be, your data set, when you collect your data, you want your data to be closer to the mean, at least within those two standard deviations, so that you can explain why, number one, why are some of the data points away from the mean? What does that indicate? But also that most of my data sits close to the average. I have a very tight data set. Because if you have data that's scattered all over the place, there's going to be extremely low probability that's going to happen. And with too much variance and variation, your data doesn't say anything. There's no story to tell. Okay. I'm going to stop here. I'm going to give you guys a couple minutes to take a break, and we are going to continue. Let me see if I can grab my. Go ahead. I'll work on this, but you guys are. Wanted to show you p-value here. So if you want, just take a break. I'll come back in 5 minutes, and we're not going to be that much longer on this, and then we'll go through some videos for graphs and things like that. I do want to show you. Okay, yeah, this is where I want to be. Okay. See you in 5. Okay, I'm back. Everyone back from their break?
Yes, sir.
Okay, great. All right. All right, so the the last thing that I want to share with you is the types of mistakes that we can make when we are looking at our data. So there are two main kinds of errors that a researcher can make when looking at their, and these statistical errors are termed as type 1 and type 2. So what do they mean? Well, you see next to this type 1, it has a little alpha sign here. So the alpha is also known as the p-value. So if you ever hear it called, you know, what is your alpha set at? They're talking about your p-value or your probability that the changes that you will see are due to chance. So the first error is known as a type 1 error or a false positive. What does that really mean? Well, it means that your data shows that there's a significant difference between two values or two groups, but there is really none that exists. So you find something even though it doesn't exist. How is that even possible? How does that happen? Well, let's say you set your alpha level a little bit higher. So you give yourself more of a cushion. So instead of setting it at 0.05, you set it at 0.10 or 10%. So then the chances or the probability that you might find, changes due to chance, it's a little bit higher. So maybe your data actually shows that it's significant, even though it's not really significant. Now, there's another story behind this, which is that even if you find a significant difference in your data, it doesn't mean it's truly significant or influential. Remember, significance is, in this case, it's based on numbers, it's based on statistics. So you could have a wonderful statistician who can massage the numbers and, put in decimal points and do all different kinds of things, and it becomes significant, but it's really not. And it doesn't have an influence in, let's say, the clinic, or it doesn't have like a broader applicability. So the type 1 error is when you find a significant difference in your data, even though one doesn't exist. And often that is due to the fact that you set your alpha or p-value level a little bit higher than what would be expected. The second one, and you notice that there's a beta here, beta is really, it stands for, or it's equivalent to what's known as power, which is how much magnitude do I have in this study? How powerful is this study? P-value doesn't do that. The p-value really describes the probability that you're going to find a difference that is not due to chance. That is the p-value, all about probability. Whereas the beta, or the power, is how much magnitude does this study have? What kind of big story can I tell with this data set? The type 2 error, or the second statistical error, is called a false negative, which means that there is a significant difference in your data set, but you can't find it. Why? Well, there's a couple of reasons. One is maybe your groups are not equivalent. So you're not really looking at the same, you're not looking at apples to apples, you're comparing apples to oranges. So you may not find a significant difference, even though one does exist between your groups. But the second one is that you set your power. Remember, we're working with 100%, right? So 20 plus 80 is 100. So we're working with 100%. You set your power at a little bit of a lower level. So instead, you set it, instead of 20%, you set it at 30. And so 1 minus your beta, 1 minus your 30 is 70%. So you won't find a significant difference because your power is not set high enough. Now, what is power really influenced by? A few things. It's influenced by the number of participants in your study. So studies with thousands and thousands of people have very, very high levels of power. Because why? There's less variance around the average, right? The tighter the data set, the more participants there are, the higher the level of power. And something else might influence your study, as not only the participants, but how are the groups made up? Are the groups, if you have a lot of subjects, maybe you're having each person act as their own control group. So they're each going through the experiment. There are various ways of doing it. So the tighter the data set, the closer it is to the average, or the closer your data points are to the average, the higher the level of power. If you set your power too low, or I'm sorry, if you set your, if your power ends up being too low, so it's 1 minus your beta, you set your beta too high, like let's say at 30, then your power is going to be lower. The magnitude of the study is going to be lower. You may also find you may not have a lot of subjects. Maybe you only have 15. And because you have 15 subjects, there might be a difference in 2 groups of 15 subjects each, but you can't find it because you don't have enough people involved and there's too much variation in your data. So these are the 2 major errors that are made, and they're important to know, and you'll see them on an exam coming up. But it's important to understand that the type 1 really has to do with probability, and it is a false positive. So you find a significant difference even though nothing exists. 1 doesn't exist. And the second error is all about power and magnitude, where you fail to find a difference even though 1 exists because you didn't set up your study correctly, or you didn't have enough participants in your study. Okay, I'm going to end here, and we're going to talk a little bit about graphs. So are there any questions up to this point? I have 2 little videos for you that we're going to view. Okay. So this first one is choosing the right type of chart. There are all different kinds of charts, and they go through a lot of them in this video. But I do think they do a nice job of kind of explaining when you would use a particular type of visual representation. And then the second one that I have is more about statistics. So what kind of tests can you run, and why did those tests make sense? Remember, in everything I talked about, you're collecting data, right? You have a data set. You've studied 150 people. You have to run statistical tests on that data to determine what story you want to tell. And that's where that p-value comes in. That's where, those equations come in, determining standard deviation. You have to run tests on those. Now, there are software programs that do that, but the idea is that raw data has to go into a test. So what tests do you run? I don't know. Like, it depends, right? You have to know what it is you're looking for, and that will help you determine what kind of tests you're going to run. And there are several tests. Many of them you could do in Excel. You can also, use other software programs that are more advanced, but there's a lot of different tests you can choose. So let's start off and just watch that first video. So does anyone have any questions before we move on? Can I get is everyone still there? Is everyone still around?
Yes.
Yes, Professor.
Great to hear. Okay, thank you for hanging. All right, so let's share the screen. Start the broadcast. Go to my video. Now, I want to make sure, can you just tell me if you can hear it?
Is the perfect
Can you hear
video
it?
if you would like to avoid creating charts like this one,
Yes, sir.
or
can hear.
perhaps this one, and especially this one.
What's the problem with these? What is the problem with this chart? Can anyone tell me?
It has too many colors.
Yeah, can you tell there's a story here? Can you see what they're trying to do?
They tried to put everything in one chart and it's confusing. Like I
Very
really need
confusing.
to focus.
Absolutely.
Understand.
Being
Okay,
able to
so
choose the
let's
right
move
type
on.
of chart for the data you are working with is not an exact science. But I'm sure you will agree something went wrong with these examples. One can't be certain whether they have been taken from a horror movie or a hippie fest. In 99.9% of cases, we don't want to show this to our audience. Charts are an opportunity, a storytelling tool, a chance to make convincing argument through visualizing data. We are not going to convince anybody if we choose a type of chart that is not the right fit for the data. To help you overcome or avoid this issue, in this video, we'll discuss A, the different types of charts, and B, the type of data they are suitable for. Bar charts. Probably the most frequently used type of chart is the basic bar chart. As its name suggests, it is composed of a series of bars illustrating a variable's development. Given that bar charts are so common, people are generally familiar with them and can understand them easily. Examples like this one are straightforward to read. However, please be aware that bar charts can be confusing too, especially if one uses them to compare several variables. I personally believe that a comparison of more than two variables with a clustered bar chart becomes too cluttered. Here is an example of a clustered bar chart that is not exactly crystal clear.
So when you look at this chart, what's the difficulty here in this chart? It looks nice, it's got a lot of nice colors. It's got a legend on the right side, kind of tells you what we're looking at, fictional book sales. These are all the different kinds of books. What's the problem with this chart?
There's too much data in that.
What
Maybe.
can't you see here? What's difficult to determine?
The exact earnings.
Well, you could see the exact earnings, but what else about the earnings is difficult to determine? I mean, you could see them, right? Like, you know, if you wanted to, you could put labels on each of the bars and look at the exact number. But what else is it about this chart?
Professor, the blue color like bar, it's difficult to compare.
Comparing what? What are you comparing?
The blue color bars every year.
Meaning, yes. Well, what about the other color balls? Can you compare those?
Like we
It's
cannot
little
compare the
difficult.
individual, like
Yeah, so-
in this case, it's like only for young adults, what is how it went per year, or how the classic fiction book sale was per year. Like, individually, you cannot, it's like too much information. So you need to be like,
Right.
if I want only of classic fiction books which were sale, then I have to be like, okay, individually color. There's too much information, basically. That's what I think.
Yes, and
Not
if you look
segregated.
if you look at each year, you could determine, you could say, oh, okay, I see the earnings of each one of these types of books. But if I ask you to tell me what's the difference between 2007 and 2009, both mystery, classics, and romance, you're going to have to like go back and forth, back and forth, back and forth. So exactly, there's a little bit too much information here, as opposed to the bar chart from before, one bar per year showing revenue or showing types of books or whatever you want to see. So there's another way to show this. So let's continue.
This isn't a horrible visualization, but it leaves plenty to be desired. First of all, it is difficult to follow the trend of all 5 variables simultaneously, isn't it? Moreover, it is hard to gain an idea about the overall state of the fiction book sales market and how it changed, which was probably what the person who created the chart wanted to show in the first place. When to use bar charts. So, bar charts are nice, but limited. We have to consider the type of data we want to visualize and the number of variables that will be added to the chart. Bar charts are great when we want to track the development of 1 or 2 variables over time. For example, one of the most frequent applications of bar charts in corporate presentations is to show how a company's total revenues have developed during a given period. A bar chart can be used to make both a year-on-year comparison and to provide a monthly breakdown. Moreover, bar charts can be pretty intuitive when we compare the development of 2 numerical variables over time. Let's say we would like to compare the revenues of 2 companies in the time frame between 2014 and 2018. When to avoid using bar charts. Simple bar charts are far from ideal in situations when we have several variables and all of them are part of a whole, such as the case in the fiction book sales chart we showed you. There were 5 categories: young adult, classics, mystery, romance, and sci-fi, all of which account for all fiction books, meaning their sum gives us the total volume of the fiction book sales market. Do we get any of this information with this bar chart? We don't. It simply shows us multiple lines, and one has to start making calculations on their own to understand how numbers developed over time. And if they have to do that, why bother creating a chart? We are better off showing the data in a table format, right? So, this certainly is one case where we should use a different type of chart. Along the same lines, a simple bar chart isn't suitable when we have a single period breakdown of a variable. If I want to portray the main business lines that contributed to a company's revenues in 2018, I wouldn't use a bar chart. Instead, I'd create a pie chart, or one of its variations. Pie charts. A pie chart is a circular graph divided into slices. The larger a slice is, the bigger portion of the total quantity it represents. When to use a pie chart. So, pie charts are best suited to depict sections of a whole. What does that mean? If a company operates 3 separate divisions, at year-end its top management would be interested in seeing what portion of total revenue each division accounted for. A pie chart is perfect for this case. However, we need to be certain that the sum of the proportions makes 100% of the total. That is, we cannot afford to forget any of the 3 divisions contributing to total revenue. When to avoid pie charts. Obviously, we can't use a pie chart in situations when we would like to show how a variable or multiple variables develops over time. Pie charts are a definite no-go in these cases. Moreover, as mentioned earlier, a pie chart would be misleading if we don't consider all values. In the context of our example from earlier, we shouldn't create a pie chart that includes revenue of only 2 of the firm's 3 divisions. Donut charts.
So when it comes to the pie chart, it is an excellent way of looking at percentages and parts of a whole, but it is not the type of chart that you will see in research. Pie charts are not used that often unless you're looking at things like demographics and they want to show it in a visual representation. That's a possibility. But I think I've seen a pie chart one time in a journal article. However, bar charts are definitely a type of chart that you will see. And of course, as we mentioned before, when bar charts get too busy, they are very, very difficult to interpret.
Donut charts are basically pie charts with a hole in the middle. It is as if their heart is missing.
I will say the same thing about donut charts. You won't see these in research, but you will see them in business. You will see them in presentations in relation to possibly your profession, but you're not going to see it in scientific literature.
When to use donut charts. The use cases of pie and donut charts are identical. The only important difference is that donut charts allow us to indicate the total amount by adding a text box in the middle. If you use a pie chart, you will have to include the total amount elsewhere, like adding it to the title. When to avoid We already explained when to avoid using pie charts. The same is valid for donut charts. One piece of advice when choosing whether to include a pie or a donut chart is to think of
Hello, sorry. Okay, I'm glad you're there. I apologize. I got knocked out. I've been having some difficulty with my Wi-Fi. Okay, so I'm back. So we were talking about the donut charts, but I don't think those are so important.
pie chart. If the value of the total is important too, then perhaps a donut chart would be preferable. Moreover, some studies have shown that people tend to get a distorted idea when shown pie charts, as larger portions can look even more so because they cover more space. With donut charts, this isn't as much of an issue.
Now,
Line
this is
charts.
where we're going to
A
see
line
a
chart
lot
is,
of
as one can easily imagine, a
lot of
line or
research.
multiple lines showing how single or multiple
The
variables
key is
develop over time.
time. Line charts are one of the best ways to take a look at how variables change over time.
It is a great tool because we can easily highlight the magnitude of change of one or more variables over a period. When to use line charts. Remember the awkward fiction book sales chart we saw earlier? Well, a simple line chart would have been way better in that case. A line chart allows us to track the development of several variables at the same time. It is very easy to understand, and the reader doesn't feel overwhelmed. When to avoid line charts. Line charts are not that great in situations when you want to show how the individual parts of a whole change over time. Yes, in theory, one could use a stacked line chart where line values accumulate, or a 100% stacked line
Let's
chart.
talk about these for a second. Most of what you'll see in the scientific literature is a stacked line chart. You often don't see 100%. So the difference is what the 100% stacked line chart shows is it highlights where 100% is, and then you can easily see where these other lines fall in relation to that 100%. And you notice it's all percentages on the y-axis, right? But here you've got, it's millions of dollars. So here you've got a dollar amount, and there is no 100% that's indicated at the top of the graph. So you're basically looking at each one of these lines representing division A, B, and C, and then how are they doing relative to one another as opposed to relative to 100%. So that's the difference in the 100% stacked line. Most likely what you'll see is a stacked line chart in the scientific literature.
Where lines accumulate to 100%, but a stacked area chart would look better.
Now, the thing
Area
is, with area charts, you're not necessarily going to see an area chart in scientific literature, but they do a great job.
Hi, this is Mark Barton at Sandy Hook Promise.
I'm gonna start it again.
And hi, this is Nicole Hockley, also from Sandy Hook Promise.
So they do a great
Area
job.
charts are very similar to line charts.
Showing the
In fact,
proportions.
at first, I wanted to show them together. However, one major confusion could have arisen. So please pay attention. The idea of an area chart is based on the line chart. Colored regions, areas, show us the development of each variable over time. There are 3 types of area charts.
Again, there's that stacked area chart, which is like the stacked line chart, and then the 100%. So here you can easily see how division A, B, and C are doing in relation to 100%. And here's how you can see how they're doing relative to one another.
Regular area chart, stacked area chart, and 100% stacked area chart. When to use an area chart? Whenever we want to show how the parts of a whole change over time, we should consider an area chart. So, for example, if the company has 3 revenue-generating divisions, it is very likely that management would like to see the development of each of these divisions. This is a great way to draw attention to the total value and still emphasize an important trend. Say, revenues from one division have been growing rapidly, while the other 2 have kept the same level. A stacked area chart is perfect in this case. However, if we are interested in the portion of revenue generated by each division, and not that much in the total amount of revenues, we can simply use a 100% stacked area chart. This will show each division's percentage contribution over time. When to avoid area charts? Obviously, similar to line charts, area charts are not suitable for representing parts of a whole over a single period. In our example, we can't use an area chart to show the proportion of revenues each division generated in, say, 2018 alone. So that's a situation where we can't use an area chart. In general, I would say stay away from the classical area chart too. It can be very confusing, and even Microsoft themselves recommend avoiding it and to consider using a simple line chart. If we wanted to show the development of revenues generated by each of the firm's divisions over time with a simple area chart, we could have something like this. I know, a nightmare. So, to recap, line and area charts function in a strange symbiosis between each other. It is recommended to use the line chart, stacked area chart, and 100% stacked area chart. We should avoid using area chart, stacked line chart, and 100% line chart. Okay, great. We are doing really well.
Now, I kind of like the stacked line chart. And again, as I said, I think it's a very easy way to see changes in a variable over time. So primarily, you'll see these a lot, as you will see bar graphs a lot, and things like scatter plots, which we'll talk about in a minute. Okay, so I am going to stop here and just also ask if you guys want to. I know it's late. If you want to hop off, you are welcome to do so. This is being recorded. If you want to hang out and stay with me, you could do that as well. I'm not going to penalize you for leaving class. I know it's late for you. It's 9:44. And as I said, this is probably the longest class of this course, but I'm more than happy to continue if you want to stay on. So I have it's roughly about 15 more minutes, but it's up to you. So if you do sign off, then good night and have a great night, and reach out to me with any questions. And if you're staying on, then I'm going to move on to the next item. So we just talked about charts and visual representation. And again, that video is a little bit more business oriented. As I mentioned, many of those charts, pie charts and donut charts and things like that, you're going to see those in professional settings. You probably won't see them in scientific literature. But when it comes to bar charts and line charts and showing your data, it's really important that you get your visual representation correct. But I will say that all of the charts that we look at will show where the average is and then how far away the other data is from the mean. So I do want to share with you something as we're looking at it. So give me just a moment. I'm going to pull up the presentation that we were looking at before. And okay, so when it comes to looking at data around the mean, I want you guys to tell me what you see. For those of you who are still here, just be a little bold and tell me what you see when you look at this chart. You broke up. Can you say it again? Sorry. Hello?
Yeah, I
Oh,
like
go ahead.
in this graph, the data is concise, like the average, the line is showing the average, and
Mm-hmm. Mm-hmm.
and the data is pretty much near the average. It's not that scattered.
Okay, good. So one thing we see is that most of the data points are around the black line, right? Would everyone agree with that?
Yes.
What other story does this data tell you? What other kinds of information can you get from this data?
Well, it's a linear graph, so it's a positive correlation that we can see in this.
What do you mean by a positive correlation? What does that mean? What do you mean?
It's like in this example itself, like as the height is growing, like with the age, the height grows. Like it's both equally growing, and so it's going upwards.
They're both going up at the same time, right? As we get older, we get taller, at least in this sample. So measuring, this is in centimeters. So as we get older, we get taller. Okay, this is known as a positive correlation. Why? Because both variables are moving in the same direction. Age and height are moving in the same direction. Great, awesome. And it's a very good observation that there are a few what we call outliers or data points that are away from the average, but most of the data points are scattered around the average, right? There are some people who are a little bit shorter at almost the age of 12, and there are some people who are maybe even a little bit taller, even at a younger age, maybe the age of, let's say, 9 or 10. Okay, good, great. A lot of information from there. Now, let's look at, let me see if I can find it. Yeah, okay. What does this data set tell you? I can make it bigger too. So what are we looking at here? This, by the way, this is pre-run, post-run. So before they run and after they run. What do you think we're looking at here?
The pre and post status.
Okay. Yep.
Sensory
What do we
condition.
mean? Okay, so what are these? I don't need the exact definition because you don't know what the sensory conditions are, but what's the 1, 2, 3, 4, 5, 6? What is that?
Those may be the number of times that they did.
Number of times or the number of experiments, right? The different kinds of experiments, okay? And then the equilibrium score is basically a test score, right? They're doing a balance test. So it's a score on a balance exam. So what does this story tell you then? What do you see here in this bar graph?
Like in the first test, pre-post, it was almost same. In the second test, it was like basically they have just told us what results that they got after doing number of tests or the same
Yes.
test, I would say, or it might be different tests and
What's the difference in test 5 and 6? What do you see? Is someone answering behind you, or is that someone just talking?
Can
So
you repeat your question, sir?
What's the difference? What does test 5 and 6 tell you about the data?
So there is all of a sudden a drop down seen rather than the first 4 tests in 5 and 6 in post test.
Okay, so how is it related to equilibrium score? What does it tell you? What's the story here?
Both 5 and 6 both have the same equilibrium score.
Okay, I might agree with that. What else does it tell you? Look at the bars. Look at the 2 bars in 5 and the 2 bars in 6. Just do 5 first. What does it tell you about the equilibrium score?
Like maybe the T sign or whatever it is the expected, and this is how much the score, something like that.
So in pre-run, the test score is higher in both cases. In post-run, the test score is lower in both cases, right? But do you see the little T's? You see these little T, these little, they call them, well, the standard deviations or error bars. You see these little error bars here? Does anyone know what these mean? What are these? Notice how they're a lot smaller.
Deviation?
Here? Yes. These are measurements of the standard deviation. So if this is my average right here, you see this is my average, this is my average, this is my average, right? The tops of the bars indicate my averages for the number of people I studied in this condition and what the score was. What happens when the standard deviation size of the entire sample size? Or the scores, I should say, of the sample size. What does that indicate to you? We talked about it when we talked about a normal distribution.
Professor, it would be more, there will be more variation from like from the mean?
Yes, greater variation. That's right. And what is that? What do you think that tells you about the data for this, for just this post-run conditions 5 and 6? What does that tell you about the data? Anyone? Let's see what they, oh yeah, here. Where's the A?
So like the spreading of the data increases?
Yes, but what it tells you about the data is if I'm looking at this bar with all of this variation here, all of this variation here around the average, can I really say anything about the comparison of the pre-run to the post-run in this condition? Can I say anything about the pre-run to the post-run in this one? No, I can't. There's way too much variation here. This data doesn't mean anything to me. It doesn't say anything about condition number 6. It says nothing about condition number 5. You want to tell me about pre-run, that's fine, but don't tell me about a comparison because the variation is huge. I can't trust that, right? So when you're looking at a visual representation, it doesn't just tell you a story of sort of comparing, you know, group to group or condition to condition. It also tells you the story of what's going on within each group or within each, you know, within each variable in this case. So in this case, I wouldn't necessarily trust conditions 5 and 6. And that's a limitation of the study. And it's, I assume, if I read it at some point, that it, you know, they mentioned that in their limitations, that they had probably a small sample size and a lot of variation in sensory conditions 5 and 6. So, all right, moving on. This is also, these are different stances that like standing, right? So they either stand on a foam surface or they stood on the ground, or I think they stood on one foot. And this was after a head injury, day 1, day 3, and day 5. So MHI is the mild head injury group, and the little square here, the squares, are the control group. So what does this graph tell us? And what kind of graph is this, by the way? Anyone know? What kind of graph is it? We just looked at it. We just went over it. I know you're tired. I know. Stay with me. What kind of graph is this? Are you still there? Hello? Are you still there?
Yes.
Negative correlation.
Still there. All right, good. What kind of graph is it?
Negatively related graph.
It's a line graph. It has lines on it, doesn't it? Right?
Yes.
What did we say about a line graph? What is it good? How is it it represents something very well. What does it represent very well? Come on. Remember, we looked at the lines and I said, this is a great graph for looking at what? All right, I'm going to put you out of your misery. It's a great graph for looking at changes of a variable over time. So if you look at this, this is day 1, this is day 3, and this is day 5, post a head injury. This is time, isn't it? Day 1, day 3, and day 5. So what are we seeing here? Well, we're seeing from day 1, we're not seeing a change from day 1 to day 3 to day 5 in the control group. It doesn't matter what stance they did, but there wasn't a huge difference. But when we look at the mild head injury group, we're looking at a lot of error being caused at day 1. And then it drops on day 3. So less errors are being made in their stance and their balance. And then on day 5, they're almost as close as they are. They're almost at the control level. So for whatever they're doing, whatever kind of training they're doing, day 1, day 3, day 5, this is really helping them in their balance after a mild head injury, right? So that's what that's saying. Now, I do want you to pay attention to something though. These little bars here are your error bars. So again, these are huge, and they speak to the idea that there is a lot of variation in the data here, both in the control group, although not as much in the control group, but in the experimental group, in the mild head injury group, there's a lot of variation. So you have to take that with a grain of salt. You have to really look at that closely and say, I don't know. I'm not sure if that's really significant, if that's a difference, you know, because you see this little plus sign here down at the bottom. These little pluses here indicate that there is a significant difference and between the control and the mild head injury group. But you could definitely question that. You could go up to the author and say, you've got a lot of variation there in your mild head injury group. I understand that there's a difference in the control and the mild head injury group, but there's a lot of variation there, and it's hard to make that argument that there is a significant difference between these groups. Okay. I am going to, let me just see if I have, okay. I'm also going to show you just one other thing before we sort of move on. And these are correlation graphs, correlation coefficients. You'll notice the scatter of the data changes as the correlation gets higher and gets closer to 1. So the correlation coefficient is the number that indicates how strong the data is either in a positive or negative direction. And the coefficient goes from -1, 0 to 1 to 1, anything over 1. Well, actually, I'm sorry. 1 is the highest. So it goes from 0 to 1. That's my fault. It goes from 0 to 1. So the closer it gets to 1, the stronger the relationship is. So this is 0. This means the data is scattered all over the place, and your exercise intensity and your heart rate or whatever you're measuring have nothing to do with each other. There's no relationship. This is a 0.4. So the ratio is a 0.4, indicating that some of the data is along the lines of the average, but there's still a lot of data points that are sort of scattered all over. This is a -0.3. So it's going in the opposite direction. It's going this way. So as you go higher in this axis here, you go lower in this one. It moves in this direction. You can kind of see it if you were to draw a line through it. This is a 0.5, so a -0.5. This is a higher correlation coefficient, but it is moving in a negative direction. An example would be, the more exercise I do, the lower my heart rate gets. So if I do more exercise, I get a lower heart rate. And you could go from high to low down here. So you could do it that way. This is a 0.6, a much better relationship. And it's definitely positive, moving in this direction. You still have some data points scattered around. This is a 0.8, which is even tighter than that, less scatter. Let's look at a 0.9, even less scatter, look at a 0.95. Everything is right around the average and the mean, okay? But this is a negative 0.95. So it's the exact same thing, but it's going in the opposite direction. And this is, of course, a negative 0.099, which is as close to 1 as you can get without being at an exact relationship. And everything is right around the mean, and it is moving in the opposite direction. So these are just some examples. Again, this is available to you for your reference to check out. Okay, how are we doing? Are we still good? If we are, I would like to share with you this video on statistical tests.
Learning statistics does not need to be difficult. Now,
and what I can do for you, if you'd like, is I'll play it on here while this is recording. You guys are welcome to drop off. I will leave it on the recording, and you can watch it after you're done. I do know it is late for you, and not sure if you guys are early birds or you're, night owls, but if you want to stay on, you're welcome to. If you want to drop off, that's okay too. So I'm going to play this. It will be part of the recording, and you will have it available to you probably tomorrow.
instead of bombarding you with complicated formulae and statistical theory, I'm going to walk you through a way of thinking, and that's going to enable you to address the most common statistical questions. When we look at sample data, for the most part we see two things. We see differences between groups, so men are taller than women, and we see relationships between variables like taller people weigh more than shorter people. And the big question is, are those differences and are those associations or relationships real? And I'm going to talk you through what it is that we mean by the term real. Over the next few minutes, we're going to take a look at a very simple data set, and we're going to see how, by looking at various combinations of variables and variable types, we can identify very specific differences between groups and very specific relationships between variables. And I'm going to walk you through when and how to use statistical tests and how to interpret your results. Now let's imagine that we have a research question, and it's about the height and the weight of people living in Ireland. Of course, we can't measure the height and the weight of the entire population. So instead, we take a random sample of the population and we measure the weight and the height of that sample. And we collect some additional information like gender and age group in a spreadsheet to set various attributes in parts. These are called variables and the object of our inquiry. Now, most data sets that you work with will contain two types of variables, categorical and numeric variables. Categorical variables, like gender, contain categories, as the name suggests. Think of them as groups or buckets that the data can be arranged into, in this case, males and females. Numeric variables, like height, are numbers, as the name suggests, and can be arranged on a number line. Now, to better understand our data and to make sense of it, we summarize it and we visualize it. In the case of categorical data, we can count up the number of observations in any given category, and we can represent them in a table and on a bar chart. And to summarize numeric data, we're firstly interested in the spread or the distribution of the data. So we might describe the range of the data, the interquartile range. We could also include the standard deviation. To get a sense of the middle of the data, we use the median, which divides the data into two equal halves, and we use the mean, which is the average. The mean is probably the most commonly used summary value to represent this kind of data. We can visualize our data using a box plot, which is a visual representation of the range, the interquartile range, and the median. And of course, we can create a histogram, and this gives us the shape of the data. So I hope you can see that this process of summarizing and visualizing the data takes it from being just numbers and words on a spreadsheet and turns it into something that is meaningful to us, something that we can get our heads around, something that we can think about. Now, in this very simple data set, we've got two categorical and two numeric variables. And things start to get interesting when we start looking at combinations of variables. So, for example, we can take a look at a categorical and a numeric variable like gender and height. And so we can group the data by gender, which is the categorical variable, and create a summary of the numeric variable, in this case height, that is separated out into those two groups. And looking at the summary, we can see that in our sample data, men are on average taller than women. What I want you to see here is that we've looked at a combination of a categorical and a numeric variable. But as you can imagine, there are other possible combinations of variables that we could have looked at. We could have looked at height and weight, which are both numeric. We could have looked at gender and age group, both categorical. And in each case, we might see either differences between groups or relationships between variables. And in each of these cases, there are specific statistical tests that we can apply to see if what we are seeing in the sample data has implications for what we think about the wider population. Can we infer anything? Is what we are seeing statistically significant? So let's take a quick look at the 5 most important combinations of data that we have. And we'll look at firstly, what might we observe in our sample data given that sort of combination of data types? And secondly, what statistical test we might apply to determine whether or not we can infer anything about the wider population. So we might look at a single categorical variable like gender, and we could do a one sample proportion test. For 2 categorical variables, we would do a chi-squared test. For a single numeric variable, we'd do a t-test. If we have a categorical and a numeric variable, we do a t-test, or analysis of variance, or ANOVA, if there are more than 2 categories in our categorical variable. And for 2 numeric variables, we do a correlation test. Now, I'm going to come back to each of these scenarios and each of these tests, so don't panic. At this point, what I want you to see is how the data can be divided up. And in just a few minutes, we're going to take each of these scenarios and work through exactly what questions you can ask and how it is that you can apply statistical tests, and importantly, how to interpret your result.
I saved hundreds with Liberty Mutual. Liberty, 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 liberty.
In a week, you'll feel better. In 2 weeks, you'll look better. In a month, you'll have a toned body.
Now, before we carry on, I just want to say a big thank you to Biomed Central, or BMC, for sponsoring this video. BMC are a publishing company that publish open access journals, and that means that the full text of all of the papers published are available for free to anyone in the world. I'm the editor-in-chief of one of the journals that they publish called Globalization and Health. I'm genuinely impressed with them as a company. I believe that they have integrity, and I honestly believe that they are making the world a better place. They have a portfolio of over 300 journals that they publish, so check them out at biomedcentral.com. I'll put a link in the description below. At this point, I want to say this. It's not good science to take a data set and just randomly stab around blindly hoping to find something that's statistically significant. Before you interrogate the data, you start off by defining your question, your hypothesis. You define your null hypothesis. You identify the alpha value that you're going to use, and then you analyze the data. So let's look at what we can do with just one categorical variable like gender. We might ask the question, is there a difference in the number of men and women in the population? Now, we could state that as a hypothesis, which is that there is a difference between the number of men and women in the population. And we could check to see whether or not we think that that is the case. And when we look at our sample data, well, we do in fact see that there's a difference in the proportion of men and women. So should we get excited? Well, no, not yet. Remember, this is just sample data. We could have, by chance, selected a sample that just happened to show a difference. So let's consider the possibility that in actual fact, there is no difference in the number of men and women in the population. And we call that our null hypothesis. And if that were true, how likely would it be? What are the chances? What is the probability that we would see the difference that we have observed, or a greater difference for that matter? And if we can show that that probability is low, then we can have a degree of confidence that the null hypothesis is wrong and we can reject it. But before we calculate this probability, which we're going to call our p-value, we must be clear about how small is small enough. Below what value of p would we reject the null? And we must decide on that cutoff before we calculate the p-value. And we call that cutoff the alpha value. And for the rest of the examples in this video, we're going to use an alpha value of 0.05 or 5%. So we've really got 2 scenarios. We've got the null hypothesis, which is that there's no difference, and the alternative hypothesis, which is that there is a difference. And the next step is to apply a statistical test. And in this case, we do a one sample proportion test, and we generate a p-value. If the p is less than the alpha, then we can reject the null hypothesis and state that the difference that we observe is statistically significant. If we add another categorical variable, in this case, age group, we may have a research question like, does the proportion of males and females differ across these groups? So our hypothesis is that the number of men and women that we observe is dependent on the age category that we look at. In other words, the proportions change or depend on or are dependent on the age category. Now we can collect our sample data, we look at it, and we can see that, yes, in fact, the proportions do change across the age groups. In other words, in our sample data, the proportions are dependent on age category. Now, is that due to chance? Well, let's test the idea that the proportions are all the same, or that they are independent of age category. That's our null hypothesis. Now here we can conduct a chi-squared test, and that gives us a p-value. And if the p-value is less than the alpha, we can reject the null hypothesis and state that our observation is statistically significant. If we want to look just one numeric variable on its own, like height, then we don't have any groups to look for differences between, and we don't have another numeric variable to look for some sort of a with. So what questions can we ask? Well, we might have some theoretical value that we want to compare our data to. For example, average height. We might have historic data. We might wonder if the current population is significantly different from that historic data. So our question might be, is average height different from a previously established height was 1.4 meters? We want to know if the average height in our current population is different to that. Our hypothesis is that there is a difference. Again, we collect some sample data. We find that the average height is indeed different from the historic height. Is that statistically significant? Well, if there were no difference, what would the chances be that we observe the difference that we do, or a greater difference? We conduct a t-test, comparing the averages, and if the p-value is less than the alpha, then we can reject the. Now let's consider categoric and numeric variable. And remember, is there between the average height of women in the is a difference? In our sample, we do observe a difference. Let's assume that there's no difference. We conduct the t-test, which gives us a p-value. If the p is less than the alpha, we reject the null, and we state that the observation is statistically significant. If we had a categorical variable with more than 2 categories, like age group that's got 3 categories, then instead of doing a t-test, we would do an analysis of variance, or ANOVA. Now let's look at the last combination of variable types in this data set, 2 numeric variables. Some real translation in here test. Test is going to give us 2 things. Firstly, it's going to give you a correlation coefficient, which tells us something about the nature of the association between the 2 variables in a minute. But of course, it also gives us a p-value. And again, if the p-value is less than the alpha, we can reject the null hypothesis.
Yeah. It's finishing up.
That we call the correlation coefficient. So let's talk about that for a second. Correlation coefficient is a number between -1 and 1. And it looks at the relationship between 2 numeric variables. If, as the x variable gets larger, the y variable gets smaller, we say that they are negatively correlated. If they are perfectly negatively correlated, then the correlation coefficient will be -1. If there's no relationship between the 2 variables, then the correlation coefficient will be 0. And if there's a perfectly positive correlation, as x goes up, y goes up, then the correlation coefficient will be 1. And of course, you can have any value in between. And by the way, it doesn't matter which of your variables is on the x and the y axis. The correlation coefficient will be the same. Now, of course, we've only just been able to scratch the surface in terms of what there is to learn about statistical analysis. If you want to learn more, then go to learnmore365.com, and I've got some courses there that you're going to love. If you'd like to learn about programming language statistics, statistical analysis. And it's free, it's very powerful, it's easy to use, it's absolutely fantastic. I have a YouTube channel that focuses specifically on that, so there's R101. Put it in the
All right.
below. Go
How many of
check it
you
out.
are still here?
Otherwise, peace.
Oh boy. Okay. All right. I appreciate you guys staying and hanging out. So, all right, we watched some videos. We went over some basic terms of statistics, and I want to open up the floor to questions if you have them. If you don't, then I'm more than happy to take questions via email. No questions? If there are no questions, then I am going to end this. Can you guys hear me? Hello? Okay. I'm going to end this, and I'm going to wish you guys a good night.
Good night, sir.
Good night. Thank you for, appreciate it.
Good night. Thank you.